What happens when neural networks are constrained by norm instead of size? When training dynamics unfold as a series of sudden neural awakenings? And when reinforcement learning pushes drones to race safely among rivals at superhuman speed? In this episode, we explore three striking papers that rethink how AI learns, generalizes, and adapts from sparse compositional theory to the hidden bias of overparameterized ReLU networks, and finally to multi-agent racing, where agility and safety must coexist. Let's explore the first paper, Learning Sparse Compositional Functions with Norm-Constrained Neural Networks. This paper replaces parameter counting with a Frobenius product norm complexity measure for overparameterized ReLU networks, and proves that norm-constrained deep models can learn sparse compositional functions without incurring the curse of dimensionality. The main approximation result shows that any Holder function h belongs to C, alpha 0, 1, d, can be approximated by a deep ReLU network with depth 2-point log 2d plus ring plus 2 and L infinity error scaling as k 2 alpha 2 plus d, d plus 1, where k is the Frobenius norm budget. So capacity is controlled by norm rather than width. For sparse compositional functions encoded by DAGs, the paper derives the first norm-based approximation rates, with error governed by the most restrictive node along a critical path and by local input dimensions .inv, not the ambient dimension d. Concrete cases include multi-index models, fx equals g, ax, binary trees, and constant depth compositional architectures. In the multi-index case, the rate depends on intrinsic dimension s and becomes independent of d, while binary trees reduce dimension dependence to log 2d. The statistical result converts these approximation bounds into excess risk guarantees for empirical risk minimization with clipped outputs. With k balanced as kn, 1, 2 gamma plus 1, the excess risk decays polynomially in n at a rate determined by local smoothness and intrinsic dimension. The analysis uses explicit network constructions for square, multiplication, and d-fold monomials, plus a norm-preserving rescaling lemma showing that shallow but wide subnetworks can operate in the fully overparameterized regime while still generalizing. Let's explore the second paper, Mildly Overparameterized ReLU Networks on Orthogonal Data, Incremental Learning, and Implicit Bias. This paper gives the first rigorous characterization of gradient flow dynamics for a two-layer ReLU network in the small initialization, mildly overparameterized regime on orthogonal training data. The main result is a saddle-to-saddle limit process as the initialization scale alpha 0 after a log 1 alpha time rescaling, the network stays near a saddle, then abruptly activates exactly one new neuron, fits a new subset of samples, and repeats. This produces an incremental learning mechanism that is absent from prior NTK style or infinite width analyses. The recursion is made explicit in algorithm 1, which computes jump times and active neurons directly from the orthogonal data and the initialization mask without simulating training. Under widths logNMX and log22, the authors prove that the accelerated trajectory converges uniformly away from jump times and recover Dana et al. 2025's interpolation guarantee. The novelty is the implicit bias theorem. Although the learned interpolator is not the minimum 2 solution once minutes to n, its squared parameter norm is still O square root n and within a constant factor of the optimal -2 interpolator's scaling. Empirically, on 64 orthonormal points in 64 dimensions with a 6-neuron ReLU network, the loss exhibits long plateaus followed by sharp drops, exactly matching the predicted saddle transitions, and the neuron norms grow exponentially with piecewise linear log norms. Let's explore the third paper, Superhuman Safe and Agile Racing through Multi-Agent Reinforcement Learning. Superhuman Safe and Agile Racing through Multi-Agent Reinforcement Learning shows that the main obstacle in physical autonomy is not single-agent control, but learning to coexist with other agents in the same space. The authors train quadrotor racing policies in Flightmare and Agilicious using recurrent PPO with LSTM layers, a perceiver-based permutation invariant attention encoder for variable numbers of opponents, league play, self-play, and a particle-based downwash model. In real-world races on a 7.5-meter split-S track with 220-gram drones at up to 22 meters per second and 7G, the league play policy beat 5-time Swiss drone racing champion Marvin Schaeper in multiplayer settings while reducing collisions by 50% relative to single-agent baselines. In 1v1 races, The policy completed 100% of trials versus the human pilot's 53.33%. In 3v1 races, it achieved 91.67% completion versus 58.33% for the human. Across 64,000 simulated four-player races, League Play delivered 23.3% crash rate versus 77.99% for single-agent training, and it remained robust up to 8 agents, where completion still reached 56%. The key novelty is that safety emerged from diverse opponent exposure rather than explicit hand-coded avoidance. The learned critic function became opponent-aware and anticipatory, enabling overtakes, yielding, and wake avoidance. An ablation without the perceiver encoder degraded performance, confirming that architectural handling of variable opponent sets is essential for multi-agent racing. That's a wrap on today's AI paper highlights. Thanks for watching.